I can release the video for it. Sorry. Yeah, good. So, okay. So we've gone through these theorems before. Remainder theorem, factor theorem. As they say there, long division of polynomials is a cumbersome process. It's therefore very useful to have two theorems called remainder theorem and factor theorem. And together, they help us shortcut a lot of things. Provide the results of a division without the division actually being carried out. In particular, the factor theorem is a simple test whether a particular linear polynomial is a factor. So, remainder theorem first. The remainder theorem is a remarkable result, which in the case of linear divisors allows the remainder to be calculated without the long division being performed. So you can see there we've got polynomial p of x and alpha is some sort of constant. Then the remainder of p of x by x, by x minus alpha is p of alpha. So that's just that principle there of if we've got, x plus 1 as a factor and we want to test that, then we would go p of -1, because remember it's the opposite of, it's the opposite of whatever this thing is here. That should equal the remainder. That's it. I'll give the remainder. If the remainder is 0, what does that tell us? It's a factor, yeah, because there's nothing left over. So it's a nice, perfect, even little thing there. Okay. They go through the proof. You don't really have to know the proof, to the best of my knowledge. But anyway, because x minus a is a polynomial of degree 1, which it is, there's a little power of 1 there, so it's a degree of 1. The division theorem tells us that there are unique polynomials q of x and r of x, q of x being the divisor and r of x being the remainder. So p of x is x minus alpha times q of x plus whatever the remainder is, and either the remainder, either r of x is 0 or the degree of r of x is 0. So the remainder isn't going to be, like x plus 2 or something like that. I won't have a remainder like that. Assuming, I could have a remainder. No, won't be a remainder like that. Yep, okay. So r of x is either 0 or a non-zero constant, and so we just simplify it as r, and they're just saying that it just comes out to be that. So p of x is x minus a, q of x plus whatever the remainder is. If we sub in alpha for x, then clearly, so p of alpha is alpha minus alpha, which results in 0, and the only thing left can be the remainder. That's essentially the proof. That's the nutshell part of it. I think so. Yeah, the remainder theorem. Yep. So that's all they're saying here. This is just that thing. Therefore, r equals p of alpha. Therefore, we get the results that we use it for. That's it. So here we go. Find the remainder of that when it's divided by that by long division and then by the remainder theorem. So we're gonna do all that out. Why not? By long division, and I've got x minus 2. And why am I doing it? Well, it's good practice for starters. So 3x to the 4 minus 4x to the 3 plus 0x squared plus 4x minus 8. Make that go a bit longer there. So x times what gives me 3x to the 4? 3x to the cube, which gives me 3x to the 4. And then negative 2 times 3x cubed would be negative 6x cubed. These all come down. That's fine. Subtract that away, 0. Negative 4 plus 6x is going to give me positive 2x cubed plus 0x squared plus 4x minus 8. X times what gives me 2x cubed? Well, positive 2x squared. So 2x cubed. Negative 2 times 2x squared would give me minus 4x squared. And these carry down. So minusing that away, and then I've got plus 4x squared, because I had 0x squared minus negative 4x squared. Yep, okay. We're all fine. And that's just going to carry down, so plus 4x minus 8. What times x gives me 4x squared? 4x positive, so plus 4x. It's going to give me 4x squared. Negative 2 times 4x would be minus 8x, and the 8 carries down, minus that away, 0, plus 12x minus 8, because I've got positive 4 minus negative 8 gives me that. X times what gives me 12x? 12. So I get 12x. And then negative 2 times 12 gives me negative 24, I think. Yeah. Minus 0, and that is going to be 32. Sorry, yeah, you're right. Positive 16, and we get a remainder of 16. And that's all they wanted. They wanted the remainder. So we would say, yeah, remainder equals 16. And then by the remainder theorem, we can just go P of 2 equals 3, 2 to the power of 4, minus 4, this is part B, sorry, this is part A, minus 4, where am I? Oh, there, 2 to the power of 3 plus 4 times 2 minus 8. 2 to the power of 4 is 16. 16 times 3, I don't know. Let's just go like that because it might cancel out. This is 4 times 2, 4 times 8, which is the same as saying 2 times 16. That's 2 times 16 plus, what's this, 8 minus 8. So they cancel out, that's fun. And then I've got 3 times 16 minus 2 times 16, which is going to give me a range 16 left over. We okay with that? Yeah. Coolies. So as we can see, the result's the same, but which one had a whole bunch more working? This one. So what are we going to do? This one. I mean, this is fun. Like, I enjoy doing this, but you know, generally we can't just have fun in when we're trying to find these things. No. Fun's not allowed. We know we're doing something wrong if we're having fun. This example 5. So that polynomial has a remainder 3 after a division by that, and has a remainder of negative 5 after a division by that. Find A and B. Complicated, but not actually that complicated once we go look at it. And I believe, did I put something like this in your end of your exam last year? It was in a test. Okay, kind of been a test. Maybe one of the quiz tests. Polynomial quiz. Yeah, I'm sure I put something like that. And if you don't know how to do it, it's like horrendous because you're like, ugh. But when you think about how to do it, it's not too bad. No, don't guess it, Check. Here's what we know. They're telling us that this polynomial, whatever it is, has a remainder of 3 when it's that. So what they're essentially saying is P of 1 equals 3. Well, what's P of 1? So then I can say 3 is equal to this with all the x's replaced with a 1. So 1 to the 4 minus 2 times 1 to the 3 plus A times 1 plus B. Cool. So what's that? That's 1 minus 2 plus A plus B. Taking those over, I'd get 3 minus 1 plus 2 equals A plus B. Therefore, what's that? 2, 4. 4 equals A plus B. Get one in terms of the other. B equals 4 minus A. That'll do. So now I've got that one. And then I get the same thing. It's a remainder of 5 after this. So I can do the same thing with that part. Come in. Welcome. No, we'll be fine. Yeah. No doubt. It's nuts out there. Okay, so first part done. I've got B in terms of A. That's helpful. For the next one, we'll just get whatever the equation is, and I won't have to get something in terms. I can just sub in B to find A. Okay. So then P of, in this case, it's P of negative 1 equals 5. Great. So that implies then that, sorry, negative 5. Thank you. It is negative 5. Correct. So that would have been annoying. You're like, what have I done wrong? And then, okay. So negative 5 then equals negative 1 to the 4 minus 2, negative 1 to the 3, plus, well, essentially minus a and plus b. Cool. So negative 5 equals 1, and then that's going to become negative 1 times negative positive, so plus 2 minus a plus b. Negative 5 minus 1 minus 2 equals negative a plus b. Negative 6 or 7. So negative 8 equals negative a plus b. So b essentially equals a minus 8. Yeah, I mean, I effectively didn't even need to do that line because I have this one here, equation 1, and now I've got 2. And then 1 into 2 implies that I've got negative 8 equals negative a plus 4 minus a. Cool. So negative 8 equal, let's move the 4 over, negative 12, a negative 8 minus 4 equals negative 2a, good, 6 equals a, which implies that b equals 4 minus 6, negative 2. And I've solved a and b. So it's just like, it's like with a measurement question where they give you the area and tell you to work out one of the lengths instead of that. That's kind of what's happening here. They're giving you the solution and asking you to work out some of the coefficients. So, and those are the two results there. So just to recap, all we did was use the remainder theorem, use the fact that I know what P of 1 equals 3, and P of negative 1 equals negative 5, and just subbed in values and solved for, did simultaneous equations, essentially. Are there any questions about that one? We've done it before. You did it last year. That's just the rule. So it's the idea is it's x minus alpha. When we have that, P of alpha equals the remainder. It's just like it's the opposite of that. So you're taking the alpha, not the minus part. The minus part is a part of the template. The alpha is the number that we want. So in this case, x plus 1 is actually x minus negative 1. And so what we wanted there was a negative 1. Sorry? Yep, okay. Sure. Yeah, if you see it, if you wanted a negative, so like they've got there, x minus 1, well, I mean, yes, correct, you're right. It's like x minus positive 1. And that's the positive one, or you just take the number. But yes, correct, you're right. That's a good way of looking at it. Factor theorem. Now I've got to try and remember the difference. But so the factor theorem tells us that P of A is the remainder after that division, but x minus A is a factor if and only if the remainder of it is 0. So this is just telling us, this is using the remainder theorem to tell us that when the result is 0, then x minus whatever that number we put in for P of x, x minus that is a factor, which there'll be no remainder, like is an actual, an actual factor. Like hurts. Okay. So that's all they're saying. So suppose P of x is a polynomial and x is a constant, then x minus a is a factor if and only if P of alpha equals 0. They're saying if and only if because it goes both ways. So x minus a is a factor if P of alpha equals 0, and if P of alpha equals 0, x minus a is a factor. That's what if and only if means. It goes both directions. That's it. There's a very quick way to test, obviously. They made a mistake in the book I think they made a mistake. The last mistake I sent in wasn't a mistake, so that's okay. They were, I would argue that it doesn't matter. Anyway, in this, you'll see that there's a few, like, they've stated the opposite of what they were wanting to state, so there's a mistake. Anyway, show that x minus 3 is a factor of that and x plus 1 is not. Then use long division to factor the polynomial completely. So we can do that once we know what the factors are. Then we can use that factor, and we'll be able to factor it out. X minus 3. Okay. Well, how am I going to test that? P of 3. So pen's died. So P of 3, effectively then just substitute 3 into every x value and see what result we get. Okay, we're working again. P of 3 equals 3 cubed minus 2 times 3 squared plus 3 minus 12. It's 3 minus 12, great. 27 minus 18 gives us 9. 9 plus 3 minus 12, clearly 0. Great. Therefore, x minus 3 is a factor. I'm not sure what the shorthand for that is. Then x plus 1, so p of negative 1, as we're dealing with x plus 1. So we want p of negative 1. Let's see what that equals. Well, that's negative 1 cubed minus 2 times negative 1 squared plus minus 1, which is just negative minus 1, minus 12. Negative 1, that becomes minus 2, minus 1, minus 12. I got worried for a second there because I was like, well, this is not equal to 0, but that's actually what they want. That's the result we're after. Negative 1 minus 2 is negative 3, minus another 1 is negative 4, and then minus 12 is negative 16. Negative 16 is not equal to 0, therefore x plus 1 is not a factor. And they said, literally, if you read in the book, they said negative 16 is not equal to 0, therefore x plus 1 is a factor. So yeah, I feel like I've picked one up there that they can't refute. Otherwise, I'm going to take issue with them. Yeah, I don't think. Results emotional stress and damages. Yeah. Okay, so then you use the long division factor to okay, so we're going to do the whole thing. My little thing's in the way. Move. Thank you. Not you. Don't you move. I just want the whole this to move. That won't let me move. Okay. So I want to click that. I just want to make some more room here, and then move this back. I'm recording the whole thing. I don't know about the internet, but you know, well, I could set up my good mic that would probably pick up everything. Well, I don't need the sound thing. I just set it up to hear everything. But then all of your little would get picked up. Yeah, just like that. Okay. This is part of the experience. What are we doing? Oh yeah, we want to factorize it. So we know that x minus 3 is a factor. Man, this has a lot of possibilities because it's negative 12. So anyway, x minus 3. We could, and here I'm going to touch on something that we're doing next week, the week after. Okay, we could. There's this theorem that basically says everything, like the thing can be divided by this and still be whole numbers. So the factors all fit into, which makes sense. If you think about if it's spread out, you've got this thing times this thing times this thing times this thing. Well, all of the numbers on the end would have to combine to be 12 in some way. So what it essentially states is that anything that is a factor of negative 12 can be an alpha or a beta or a gamma or whatever those sort of things are. Yeah, so what it means, it doesn't mean that they are, but it certainly means that anything that's not a factor of those things, for instance, 7. 7 is not a factor of 12. X minus or plus 7 cannot be a factor. X minus or plus 6 could be. It might not be, but it could be, because 6 is a factor of 12. Okay. Well, it might be, I don't know. Let's have a look. Let's do the thing. So x minus 3, and then we're going x to the 3 minus 2x squared plus x minus 12. Because we haven't got to that theorem yet, so we have to still do it the long way. X squared, I'm going to try and do this just as quickly as possible. X to the 3 negative, so minus 3x squared. Come down, minus that. It's going to be plus, so it's x squared. Just check my working as we go along. plus x minus 12. That's going to be plus x, gives me x squared, minus 3x, that comes down, oops, not 0, minus 0, that becomes a plus, so plus 4x minus 12, that's going to give me plus 4, and then I got 4x there, negative 3 times, which is negative 12, and 0. Right. So then I know that p of x equals x minus 3, x squared plus x plus 4. Can I factorize that any further? I don't think I can, no, because two numbers multiply to give me, well, I could just look at the what do you call it, the discriminant. 1 squared minus 4 times 1 times 1 is, it's negative 3, equals negative, therefore that's factorized. So the discriminant, delta, is equal to b squared minus 4ac, and in this case that's saying 1 minus 4, which is negative 3, which is less than 0, therefore no other real factors. So that's our solution there. Well, I can clearly see that what value of x in this first one is 3, so that works. Here, you can just individually factorize that, and we can't. That's as simple as it gets. So that's fully factorized. Yeah, the only solution for that is 3. There's no other real value. Did that answer the question? Then use long division to factor. Yeah, okay. Now remember the difference between this and then actually showing the division. So we factorized it, we haven't divided it. Remember, that would be going over x minus 3 over x minus 3. Cancel, cancel, so on and so forth, right? So we know that p of x divided by x minus 3 is x squared. What did I just do? No, that's fine. Is x squared plus x plus 4. That's all. So there's just bear in mind that you're either factorizing or you're actually doing a division. In this case, we've used long division to factorize, and that's showing it in factored form, i.e. as opposed to expanded form, which is what it was in. And that's it. Yeah. Okay. Factoring the polynomials, the initial approach. Oh, okay. So I think this is doing that thing now. Possibly, let's have a read. Factor theorem gives us the beginnings of an approach to factoring polynomials. This approach will be further refined in the next 3 sessions. So this is about where we can effectively use the factor theorem to avoid doing the long division process altogether within reason. Yeah. Okay. So what we're effectively doing is using trial and error of x minus a to find p of x, which of x equals alpha, sorry. To find p of x, and then we use long division to factor p of x into its form, which is like, that was that result we got back up there, right? We had x minus alpha and what we've effectively called q of x? Yeah, q of x, the polynomial q of x, because that's the quotient. That was the leftover part. If the coefficients of p of x are all integers, then all integer zeros of p of x are divisors of the constant term. And that's that thing that I was explaining before. So assuming that every coefficient here is an integer, so not a fraction, which it is, that is the case. Sorry? Yep, integers are all the negative and positive numbers, and 0. Yeah, the only question about 0 is whether it's a part of the whole numbers or not. I don't know. Thanks, Nathaniel. So they are then all integer zeros of p of x which are those, the linear terms, I guess, are divisors of the constant term. So that makes sense because what was our integer 0 here? 3. Over there, it was 3. And 3 divides 12. Or negative 12. What is it? Negative 12, yeah. 3 divides positive or negative 12, it doesn't matter. So whatever factors we get, and then we use that. This is the proof for it. I wouldn't get too caught up in it. But essentially, that's the proof. So if we have p of x, and then we know that all polynomials can be represented in this form, we've got an, some constant term, and then some other coefficient, so on and so forth, as we get down to eventually, something with a degree of 1, and then degree of 0, the constant on the end, a0. And then that's all the coefficients, and they're all integers. If we let x equal alpha and be an integer 0 of that, so we're assuming that that does divide. So x minus alpha divides this whole thing, meaning that there's not going to be a remainder after it. Then if we sub in that value, p of alpha equals 0, and we go ultimately this whole thing equals 0, then we can effectively say that if I move this one to the other side over here, or rather move everything else to the other side, so all of this comes over here and becomes negative, so it's negative of all those, and then we could divide an alpha out of it, right? Because remember, alpha has been replaced, all of the x's are replaced with alphas. Divide an alpha out, I factored an alpha out, it's out the front now, and therefore a0, it says, so a0 is an integer multiple of alpha, because technically alpha is now a factor of a0, which was the constant that was on the end. It's not the easiest thing to comprehend, but using it is really easy. And you can take the general gist of it is simply that these alphas, betas, whatever they may be, have to be factors of the constant, which is great because that limits all of those possibilities. Instead of possibly having 1 to 100 or 1,000 or whatever the numbers are of possible alphas and betas and all of those numbers, all of those zeros, then we can limit it to factors of the constant. Cool. So we're going to factor this completely. Okay, well let's test. It is a factor. Okay, so p of 1 gives us 0. You're saying that unequivocally, Nathaniel? Okay, equals 0. Okay, equals 0. So therefore, x minus 1 is a factor. Well, let's keep going. Our constant here is -4. So all of the possibilities are effectively 1, -1, 2, -2, and 4 and -4. So those are all the possibilities. So let's try that. So p of -1, what does that equal? -1 to the 4 plus -1 to the 3. Well, those are going to cancel each other out. I can see that straight away. Oops. And then minus 9, -1 squared, so that's just -9, that's fine, plus 11, -1, which is effectively minus 11, and minus 4, well, that's not equal to 0. And I don't actually need to know what it is. I just be like, yeah, that's not 0, let's leave it at that, kind of thing. Let's go p of 2. P of 2 is going to be 2 to the 4 plus 2 to the 3 minus 9 times 2 squared plus 11 times 2 minus 4. Did you do this one, Nathaniel, in your head? No? Okay. Okay. Well, what's that? That's 24 minus 36 plus 22 minus 4. What do we get there? 12, -12 plus 22 minus 4. Yeah, not equal to 0. Cool. So we've lopped off, so we know that one is, that one's not. Oh, yep. That one is not. Oops. Let's try with -2. So P of -2. And it seems like this is long and arduous, but it saves us doing a long division each time. Yeah, this is quicker. Because what's the result after we do that? We're going to have a cubic result, which we're then going to have to do another solving for. So if you're starting off with a polynomial of degree 3, then yes, because you only have to do one long division, and then you can, factorize the quadratic, because that's really easy. But if we're starting off with a power of 4, then we have to, find that, x minus 1, divide that out. I'm going to then have a polynomial of degree 3, which I'm going to then need to do this test again for, and then divide it through again. So I'd have to do 2 long divisions. So this is still quicker than doing 2 long divisions, I think. Okay, that one. So -2 to the 4, -2 cubed minus 9, -2 squared plus 11, -2 minus 4. Okay. 32. Is that right? No, hang on. 3 is 8. Oh yeah, 16, thank you. 16 minus 8, good. Minus 36, minus 22, minus 4. I think that's going to be not 0. Yeah, okay, so now P of 4, let's try. Oh, 4 to the power of 4. That's exciting. Plus 4 cubed minus 9 times 4 squared plus 11 times 4 minus 4. Yeah, good observation. So, what's 4 to the power of 4? Could be, yeah. 4 squared is 16, then times 4, 64, times 4 again, 256. Yeah. 64 times 4? Yeah, 256, yeah. So 256 plus 64 minus 9 times 16.
Attention, all year 9 and 10 students, please line up outside design and tech. All year 9 and 10 students, please line up outside design and tech. Thank you.
Think, 144? Yeah, I mean, this is clearly getting, what's this? 320, thank you. Minus, what was this one? Okay. No, we can't do that. Well, maybe, but it's dangerous to do a subtraction before we've done this thing here. I think it's okay in this case, but sometimes it doesn't work. Okay, so yeah, not equal to 0. That's fine. We established that. P of last one, P of -4. I want to just make that a bit smaller. Squish it up. Cool. Now, here's the thing, writing all this out is tedious, but if you set up in your calculator the whole, the equation, and you just have to go through and change the number each time. And you could do this in like 2 minutes, like at most. Not really. I mean, if you make a mistake, sure, but like in the sense of you could just go, yeah, P of 2 is, it's not equal to 0, so on and so forth. That's fine. You don't have to show all this. This is just adding and subtracting. You need to show each of the results. I would show each of the results, but for sure on your calculator, get the template set up and then just change the numbers each time. It is cool. Well, I want to do this one now. So -4 to the 4, which is obviously going to still be positive 256, plus -4 cubed. Yep. minus 9, negative 4 squared plus 11, negative 4 minus 4. Okay, cool. So this was 256, and this was minus 64, and this is minus what? Minus 44, minus 44, minus 4. Wow, interesting. Cool. Equals 0, therefore P of x plus 4 is a factor. All right. So here's the part here where we actually are going to have to do a long division. Apologies, but this is where it gets a little bit interesting, because what do I actually know are both factors? Well, x minus 1 and x plus 4. Yeah, so effectively, and what is that? That's x squared. Sorry, x minus 1, is it? Okay. Plus 4x minus 1x, so plus 3x minus 4. X squared plus 3x minus 4. And that is a factor, which means I multiplied x minus 1 and x plus 4. Yep. Because I want to do a long division of what I know to be a factor. Remember, if those two things are factors on their own, multiplying together, that result is a factor too. You're just reading ahead. Okay. What was the initial question was x to the 4. Has to be. Yeah. Well, okay, two factors that we know of are of a degree less than the polynomial that we're dealing. Sorry, the question was, how do we know if two factors multiplying together will also be a factor? Those two factors multiplying together are of a lesser degree than the other one. So it's like, say I had 24, and some factors of 24 are 3, 2, and 4. I think there's or 3, 2, and a whole bunch of 2s, right? So any combination of those are also going to be a factor of 24. Yeah, you need to look at the combinations though of the factors. That's a good point. But like if I break it down, 8 times 4 would be a non-equal combination. So if I break 24 down, it's 2 times, or what is it? Hang on, let's go. It's 6 times 4, and that can be broken down into 2 times 3 times 2 times 2. So if I borrow this one and this one and this one to get 8, then all I can multiply it by left is 3. Okay, so I can multiply, but we're after factors, right? So I can pick these two, that's 6, that's a factor of 24. I can pick these two, that's 4, that's a factor of 24. I can pick these 3 times 2 is 6 times 2 is 12, that's also a factor of 24. And I can pick these 3, 8 is a factor of 24. What you've done there is, yes, 8, like 8 is a factor of 24, but then I can't multiply that by something that's not left over being a factor as well. So in this case here, this is a factor, and this one is a factor, and because the degree is less, I think that's what allows it to happen. If the degree was more, obviously no, and then yeah, like it's just, we don't know what that remaining thing is, and if I picked these things, I mean, we'll easily be able to tell, because if it's not, it won't give us a result. Like it won't work. Like I have here. Yep. Yep. That's just going to give us that again. Yep. Yep. Yeah. Well, I mean, we know straight away, like what Michael said, we've got this factor here, x minus 1, and we have this factor x plus 4, but the degree of those multiplying together is only 2, and we need a polynomial of degree 4. So we know we're missing you know, two things. And we also know that there's no more linear factors because it didn't work. None of the other tests worked. So there's no more linear factors. So our result is going to be a quadratic. Yeah, which makes sense. By dividing a degree of 4 by a degree of 2, we should get a degree of 2. I think we should always get. Anyway, let's try this. I've got, what was it? X to the power of 4 plus x to the power of 3 minus, I've got it written somewhere, plus x to the 3 minus 9x squared, and then what? Plus 11x minus 4. Yep, okay. So x squared is going to be x squared. That's great. Gives me x to the 4. 3x is going to be plus 3x cubed minus 4x squared. These come down. Oops. Do our subtraction. 0. X cubed minus 3x cubed is going to be negative 2x cubed. That's effectively negative 9x squared plus 4x squared, minus 5x squared plus 11x minus 4. Negative 2x minus 2x is my next thing. So negative 2x cubed. That times negative 2x is going to give you minus 6x squared and plus 8x carries down. 0. Negative 5x minus negative, so it's plus 6x because it's going to give me positive x squared. 11 minus 8 is plus 3x and minus 4. I can clearly see, what do I times x by to get it to be that? 1. So plus 1 on there is going to give me, you know, all these things. X squared plus 3x minus 4, 0. Great. So that's my remaining factor there. Get it going. I need to, no, not that button, that one. I need to make more space. Thank you. Okay, so my results then for P of X are X minus 1, X plus 4, and X squared minus 2X plus 1. And does that factorize? No, there are no two numbers that will, oh wait, good. Okay, oh actually I want to keep that there. So that's an interesting point. So we've got x minus 1, well, in a sec, x plus 4, and then this does multiply out to be x minus 1 squared, which gives us x minus 1 cubed, x plus 4. So, sorry, which I would rewrite actually as x plus 4 x minus 1 cubed, because I'm pedantic. Yeah, that little cube there was separating the brackets, and I don't like brackets separated. So that's done there. So what our problem was there is we realized, oh yeah, x minus 1 is a factor. Turns out it was a factor of degree 3, one of those big ones. And we may explore how we can be certain of those at some point, but I'm not sure. I don't know. We'll see what happens next week. That is it. The next 3 sessions will develop methods that will often allow long division to be avoided, often but not always. So in this case, yeah, that was the end result, which is pretty cool, I thought. Okay, we done? Any questions about that? No, it's not really. It's just a different approach, and frankly, when you're doing it with a calculator, it's a much quicker approach. Like I said, you don't need to show all of this working for every one of them. Just make sure that when you enter it in your calculator, you've got brackets, you're doing your positive and your negative numbers correctly, and then you just change that number each time, and you can have your test done in like 1 or 2 minutes. for all of them. And then, you know, if you get if you get your factors of a degree less than your polynomial, then you'll know there's either a double up or there's a quadratic or a cubic result, whatever it may be. Yeah, that's all. Okay, that's it. We'll stop it there. Only 45 minutes. Boom.